Now remember this. We are not looking at the temperature. We are looking at the heat being radiated. It is the apparent heat, not directly the temperature. The heat can be seen in the thermal imaging device, and we can measure that heat by the device because we understand the formulas of how it's being given off. But you need to understand the conductivity. You need to understand the emissivity. If you have your emissivity off, you could be considerably off in the temperature that you indicate is, and that is of course the rating of the problem. The seriousness of the problem is determined by that. So it is the apparent temperature, not the actual temperature, that you're looking at. So when you're viewing it through a thermal imaging device, realize it's the kinetic energy transferred by conduction to the surface and then radiated out to the imager. We will express that as a temperature, but it's the apparent temperature. You're actually seeing the energy given off as radiation. Let's review again the three methods of heat transfer. The first is conduction, the transfer of heat between two parts of a stationary system caused by a temperature difference between the parts. Okay, again, zeroth law, second law. It's going to flow down a thermodynamic gradient from one to another until it gets to equilibrium, if it does. Okay, it is the transmission through a conductor. It's the thermal conductivity, is the ability of a substance, a mass, to transmit heat, to pass that heat from one part of that system to another, which depends on the atomic structure, the molecular structure of the mass itself, the physical state the mass is in. Is it, if we're talking here about conduction, you're talking about a solid, mostly. Sometimes you're talking about a fluid, such as water, which is pretty dense. So it conducts and it convects. At the surface it radiates. Okay? But conduction is when you're passing vibrational energy from one molecule to another. That's what it is. Convection does the same, but it does it through air. And in convection, the transfer of heat by circulation, the heat moves up because the hot particles move up because they're farther away from each other. They become less dense and more energetic. The liquid or gas, the colder molecules move down in the system. Okay? If you're in your house and it's warm, you turn off your house fans, you'll note there's a temperature difference between the floor area and the air in the upper area, especially if you have a vaulted ceiling. You're going to notice the difference in those. Okay? That is convection. That is the cloud that we saw much earlier in the series. We saw a cloud that was convecting upward, where the moisture and the air was that was warm was convecting up thousands of feet into the air and convecting down as it cooled off, lost that energy and cooled off. Now it's very complicated. It's not that simple. Every molecule bumps into another and it can go up and down at any given second. But that in general, that's what happens. It happens reliably enough to generate that cloud and have it rise high. It's reliable enough that we can make a convection oven, push that heat around and heat up your food more quickly. That's convection. Okay, the molecules bump into each other, speeding one up and the other down. Again, now we're back into Boyle's law. Okay. Radiation is the third method of heat transfer. Radiation is the process in which energy is emitted as particles. Thermal energy is transferred through a medium to a different object by absorption of that electromagnetic radiation given off by one. So one object will emit infrared, the other one will absorb it. This is what you feel when you put your hand in front of a heater and you can feel the heat. The heat is being given off as thermal radiation. Often in this case it's hot enough to get into the actual red range, sometimes hotter than that, but that's radiating out. It's radiation that's hitting your hand. Your hand molecules are being excited, they're moving faster. Your nerves say this is warm. Okay, so that's radiation, convection, and conduction. But there's more to it than that, isn't there? Because when it conducts to the surface, now you have to deal with emissivity. Emissivity is, of course, that ratio expressed as a dimensionless number that compared to a theoretic black hole that tells you how much of that energy is reflected internally or externally, and how much is emitted as radiation. Now, the opposite of that is absorbency. Absorbency is the rate at which electromagnetic radiation strikes a surface and then is absorbed is reflected back in the direction it came from. Actually, it's angle of incidence versus angle of reflection. So if let's say light strikes a mirror at 30 degrees, it will leave in the opposite direction at 30 degrees. So angle of incidence, is equal to the angle of reflection. Okay. But that brings an interesting aspect, and that's the last point on this slide, is that emissivity changes by temperature, wavelength, shape, and surface conditions. Wavelengths is what we're talking about here with a mirror. Well, I can radiate a mirror, and most of that heat will be absorbed by the mirror itself, that is, move through that shiny surface on it's called silvering. That's used to use silver or different metals to pass through into the mass of the mirror. Almost all of the visible light is reflected off. So there's a difference in how a given mass handles each wavelength of light. Now here we're only talking about infrared, so it's all going to be handled pretty much the same. We can depend on those emissivity charts to tell us how much is being given off. But this also explains how, if you're looking at an electric contact, let's say there's three of them, you're looking at a three-phase system. There's phase 1, 2, and 3, or if you're under the UK system, or which is what they use in the Orient, it will be phases A, B, and C, actually lined up on a device in the opposite direction. So left to right would be CBA instead of the American system, 1, 2, and 3. And each of those has a marker on it that is, let's say, black, red, and white. Then that device, that insulation, might look a little bit different in each case. You have to understand they might have a different emissivity according to the materials that are used to mark the device. Just as that black plastic insulation is going to be different from the shiny metal contact that you're looking at. So again, in thermograms, sometimes it looks like the insulation itself is the hottest spot when it may be the difference in emissivity. If you have a brand new shiny, let's say aluminum contactor that's put on, but it's put on improperly, it's loose, it's going to start radiating heat. More of that heat's going to be given through that insulation, even though it's a poor conductor. Sometimes more can be given through that insulation than the contactor itself, until it gets hotter and starts to oxidize. So you need to understand emissivity and how it applies to each small piece of the picture that you're looking at, because it can change from piece to piece, condition to condition. The desalination device that I showed in an earlier presentation, it was made of 316L stainless steel, which has a low emissivity. So we had put a spiral scratching on the device to make a pattern out of it, make it look nice, a swirl design on it, and all this. That increased the emissivity that it gave off. But in order to do our testing with a thermal imaging device and with a thermometry, that is a thermal temperature device, we had to know exactly what we're shooting, so we painted black enamel paint on it so we knew exactly what the emissivity was. Otherwise, when you're dealing with large amounts of energy, those numbers would have been significantly off. And here's what we mean. You'll notice that the black enamel paint has an emissivity of 0.8. It's about in the middle of this chart. You've seen this chart before. It's important to not to memorize all of it, but to understand the concept, but to know those things that you're looking at. So that's why we painted that device, which you'll see in a minute again. You'll see me reflecting off of it. Why we painted black spots with enamel paint. We knew exactly what the emissivity was, could make our measurements and metrics of how much energy was being used accurately because of that. Okay, but look again what happens with highly polished aluminum with an emissivity of 0.139, or about 4% of the energy that hits the surface actually leaves. The rest of it stays inside. If you are reaching out towards a device to see if it's warm and it's made of something like a shiny metal, specifically a silver-colored metal, and that's why they use silver coloring on the back of a mirror. If it's a silver-colored metal, most of the energy is reflecting back inside the device. It's not being given off as emitted radiation. So as you approach your hand and put it up to the device to see if it's warm or not, it might not feel warm until you contact it and you become the conductor. And then it's going to give off 98% or so of the energy into your hand. It's going to get very hot very quickly if it is in fact hot. But you'll notice the temperature difference even if it looks cold to you. If it looks like it's maybe in the, say, the 50 degree Fahrenheit range, and it's actually 90 or 100 degrees, your fingers will tell you much more accurately. That's why often in the kitchen, pay attention to what you do. Often you put your hand towards something to see how much heat is radiated. There's still that quality of heat that you can measure. You can't measure the quantity, and then you'll touch it quickly just in case it's too hot, so you don't transfer much heat into your finger, and see if it's hot. Then you'll touch it a little bit longer and a little bit longer and a little bit longer until you find out how hot that was. Okay. The imaging device is like that. Now look at the copper. When polished, again, it has an emissivity of 0.023, very much like the aluminum, but when oxidized, it jumps to nearly 8. That's quite a temperature range. Okay, so it will emit much more light, 80% of the light. That should be, of course, 0.80. 80% of the energy that hits its surface when it's oxidized will leave its surface. Now that's good for heat transfer. It helps you get rid of that heat, but it also tells you, of course, that's oxidized. It's heating up the devices around it. There's a problem that needs to be fixed. Many conductor devices that you will see are made of these metals, and herein lies the issue.